In this video, we're going to continue Chapter 4 by looking at the Thomson model and the Rutherford model of the atom. Here are these two, numbers 2 and 3 in the chapter. In a previous video, we talked about Dalton's model. Now, we're not going into great detail about the experimentation that they used, but rather we're looking at what they contributed to for our understanding of the model. There are mathematics and physics and all sorts of interesting things that go along with these models, but for the scope of our introductory course, we're going to look at just some of the contributions that help us understand the atom better. So in this illustration, which you can find in your Canvas, it lays out some of the models, the people who are associated with the contribution, and then some of the things that it added, and then some of the things that it was missing. And so in the previous video, like I mentioned, we looked at Dalton's model, which was in the early 1800s. And now the models we're going to take a look at now are in the early 1900s, so 100 years later. Now, in order to understand things about the atom, we just need, for our situation, to know some of the properties of electrical charge, because electrical charge was used in the discoveries. And so here's some things that we need to keep in mind, not just for this chapter, but also when we talk about bonding. When we say charge, we're talking about something that either has a positive charge or a negative charge. So we'll think positive or negative. Now, a very important idea with charge is number 2, opposites attract and like charges repel or push away from each other. So opposite charges attract means that positive and negative charges would be drawn toward each other. Like charges repelling or pushing away means that a positive and a positive next to each other would actually push away from each other, or you could have a similar idea if you had a negative charge next to a negative charge. So when they're the same charge, they push away from each other. When they're opposite, positive and negative, they attract each other. Now, charge number 3 can be transferred from one object, either by the contact of those objects or what we call induction. So charge doesn't have to be stationary, it will move. And number 4 says the force of attraction. So how much two charges are attracted to each other is related to their distance. So the farther apart, the less attraction. Let me just write that. So if they're farther apart, this equals less attraction. And if they were closer together, this equals more attraction. And we could also say this in terms of the repulsion of like charges. So the closer two like charges are together, the greater they repel each other. And the farther apart two like charges are together, the less they repel each other. So we just need to keep a few of these ideas of electrical charge in mind for this chapter and for when we talk about bonding. So let's get into the Thomson model, and this is in 1903, J.J. Thomson, who was a British scientist. I always like to just put a little asterisk when we talk about models that are designated for one person. In science, it's often that there might be a lead researcher, a principal researcher, and then that researcher has a group of people that are working together toward, discovering things. So often the lead person gets their name on these type of things, but it's in most cases, I'm sure there's some where there's just one person, but in general, in science, it's a team oriented thing. Not always pleasant, because it's like a soap opera if you're interested in science history sometimes, but it is a team thing. But anyway, with that said, I just like to let you know. And the other thing is, Thomson probably wasn't the only researcher, working on discovering things about the atom. In fact, I know he wasn't. And so sometimes it's a race for information. Okay, so back to Thomson. So Dalton's model did not account for anything smaller than the atom. So Dalton had just a sphere, and the atom was the smallest form of matter. And I'll come back to that, because in chemistry there is something interesting about the atom. So I'll come back to that in a little bit. But what Thomson proposed is that there were actually smaller charged particles inside the atom, or that composed the atom. So he used attraction and repulsion in his experiment, and in this he determined that there were positive and negative charges. So what he came up with was the illustration that's on the bottom right hand of the screen. So it's not quite what we think of now. It's called the plum pudding model, and you can Google plum pudding. It is an English dessert. It's not really pudding. To me, it looks more like cake with I guess pieces of plum, but like raisins or currants, or like it has like that fruit in it. So Google it if you're wondering why would they call it a plum pudding. It's not really pudding. But how we envision it is that the atom is positively charged. So it's like a soup of positive charge. And then embedded in it are electrons, and he didn't call them electrons, but we call them now negative particles that are embedded into this positive atom. And so if positive and negative equal each other, the overall atom is neutral. So let me just write that down, because that is an idea that we will continue to think about. But if the positive charge equals the negative charge, they cancel each other out. And so overall, sorry, the writing's so messy. It's neutral. So that's another idea we use quite a bit. So you can see Thomson added the idea of having charged particles inside this atom. So it's no longer a sphere. There's something we call subatomic. Up here you see the word subatomic. Sub meaning like below or inside the atom. And so now we've added particles, and this was in the early 1900s. So we have subatomic particles. Well, this idea of subatomic particles continues, but the plum pudding model does not. So in around 1911, 1906, 1911 is when the model is kind of earmarked, like it's kind of the year. Let me back up. Let me just say here, I don't have you memorize specific years. So I would like you to know, like Dalton's model was first, and you can, about a century later, then we have a Thomson model, followed now by Rutherford model. So I would like you to know the chronological order of the discoveries, but you do not have to remember the specific years. That won't be important to what we need to accomplish. So here's a really cool experiment, and I don't normally show experiments, but I think this one is so cool. So this is called the gold foil experiment, and the reason it's called gold foil is because he used a piece of thin gold foil, and what they did was they fired, you can see here they're called alpha particles. And alpha particles are radioactive particles, and they have a positive charge. So he was firing positive charge into this thin gold foil. Now, what they thought with the plum pudding model is if the plum pudding model was true, so they were trying to test it, then the alpha particles would just blast through that positive soup and just continue on to the other side. So it would just not get turned anyway. It would just be a straight line of particles. And you can see down here is what they kind of expected, that they would put the alpha particles through. Someone, you would think positive would deflect positive, but someone described it as the alpha particles were large, and so it would be like throwing a baseball through tissue paper. So they were thinking that alpha particle would just blast through the paper and go to the other side if the plum pudding model was correct. But if you look up here at this illustration, what you'll notice is that not all of the alpha particles went through. So they scattered, they were deflected, they got put into different directions. And this big ring around it, you can see here, it's a screen. That's what they were using to detect. So it could detect when the particles hit it. So with this experiment, their hypothesis that if it was the plum pudding model, it should all go through undeflected did not occur. So now they have to back up and think, okay, so that the hypothesis, like that wasn't correct. So how can we explain what we observed? So let's look at his model. So he came up with a nuclear model instead. So what he said is, because, and I'm going to go back to the other one, and they didn't call them protons and neutrons quite at this point. But what he said is, okay, instead of having a proton soup, instead of that, all the protons are in a cluster in the center. Now, they did not have neutrons. I got this illustration from a different textbook. There were no neutrons in Rutherford's model. Okay, they did not know about that yet. So for him, it was just the positive charge in the center, surrounded by much smaller negative charge electrons. Okay, so let's look. I want to look back and think, why would he think that? So if I look back to this model, and let me erase my previous lines. So what was happening is, instead of going, if we had, I'm going to draw an atom when this is the plus in the middle. So the plus charge, for the most part, would just go through because the atom has a lot of empty space. So the plus charge would just go through. The electrons are really small, so this alpha particle would just go through. But every now and again, the alpha particle would approach this positive, very concentrated positive nucleus, and if it hit close on, it would deflect backwards because like charges repel. If it came in and was close to it, but not maybe hitting it, the repulsion would deflect it and it wouldn't be able to keep going straight. So that's what now they're imagining as the model of the atom, a center that has a tight positive charge, and then surrounded by the space where the electrons are. So, and you can see here, I put a little asterisk. The neutrons weren't discovered at this point, but because of his results, Rutherford did predict that there were other particles inside the nucleus because it was so large. So the idea that there could be a third particle that we call now the neutron was in the back or in the front of their minds. They were thinking, okay, there's something else there. but it wasn't discovered until 1932, which was about 20 years later. And if we were in class, I would ask you why, and maybe you can pause the video and think about why. I'll tell you the why. It's because the neutron is a neutral charged particle, and so they were working with charges, the positive alpha particles, and so Thomson was working with some negative charge, which the neutron didn't interact with. And so it took a little bit longer until technology and their instrumentation maybe caught up so they could do experiments to figure out. They really started understanding the neutron more when they could determine the mass of atoms. And so it took a little bit longer. So they knew something was there, but it took a little bit longer. And so we have this nuclear model of the atom, and this is where we land. And as chemists, this is the model of the atom that helps us understand some of the bonding and some of the properties. And so in our next video, we're going to talk about the particles, the protons, the neutrons, the electrons, how they help us understand what's going on, some of the properties that that are attributed to them. And so we'll look a little bit more into that. The evolution of these models up to the nuclear model is very interesting, and I know if you want to find out more, there's a lot more online that you can discover.